In the 72 hours after you die, 6 laws of physics will dismantle your body in a precise and predictable sequence, each gradient collapsing at a rate determined by how much energy it costs to maintain. The most expensive systems fail first. The cheapest persist for centuries. The order never varies. And it reveals something extraordinary about what it costs to be alive. A living body is what physicists call a dissipative structure, a system that maintains its order only by continuously consuming energy. A hurricane is a dissipative structure. A candle flame is a dissipative structure. Remove the energy, and the order does not coast. It collapses. A living body maintains dozens of these gradients simultaneously: thermal, mechanical, chemical, electrical, biological, every one of them costing energy every second. Death is when the energy stops. And what follows is gradient by gradient collapse, each one at a rate you can calculate, in a sequence determined by the energy budget of the system. To understand what happens when the energy stops, you first need to understand the energy. The molecule is called ATP. Your body produces roughly its own weight in ATP every single day, 40 to 70 kilograms, manufactured and recycled continuously. But you do not store it. The total amount in your body at any moment is roughly 250 grams, about the weight of an apple. That tiny reserve is consumed and regenerated so rapidly that if production stops, it is exhausted in seconds to minutes. ATP is produced by using the oxygen you breathe to extract energy from the food you eat. When the heart stops delivering oxygen, that production ceases. Within minutes, every energy-dependent process in the body begins to fail. The pumps that maintain the electrical charge across every cell membrane, the motors that move molecules from one compartment to another, the repair systems that fix damaged structures, all of them require ATP, all of them stop. And the first gradient to collapse is the thermal gradient. The thermal gradient exists because a living body is a heat engine, one that consumes chemical fuel and radiates roughly 80 watts of continuous thermal power, the output of an incandescent light bulb, every second of every day for your entire life. That is why you are warm. That 80 watts is not optional. It is the minimum energy cost of maintaining the chemical reactions that keep you alive. The pumps, the motors, the synthesis of new molecules, the repair of damaged ones. Roughly 60% of all the energy you extract from food is released as heat. Your temperature of 37 degrees Celsius is not a passive property. It is actively maintained by burning fuel, regulated by a thermostat in the brain that adjusts metabolic rate, blood flow to the skin, and sweat production to keep the core temperature within a fraction of a degree of its target. When you die, the engine stops, the thermostat stops, the heat source is gone, and the body begins to cool. This is called Rigor Mortis, from the Latin algor, meaning coldness, and mortis, meaning of death. The physics that governs it was worked out by Isaac Newton in 1701. Newton's law of cooling states that the rate at which an object loses heat is proportional to the difference between its temperature and the temperature of its surroundings. The greater the difference, the faster the cooling. As the gap shrinks, the cooling slows. The result is an exponential decay curve, rapid at first, then progressively slower, approaching ambient temperature asymptotically. The mathematical form is a first-order ordinary differential equation. The rate of change of temperature equals a negative constant times the difference between the object temperature and the ambient temperature. The constant depends on the thermal properties of the object and its environment. For a human body in a room at 21 degrees Celsius, the cooling rate is approximately 2 degrees in the first hour and roughly 1 degree per hour after that. This is a simplification. The actual curve depends on mass, insulation, and surface contact. A large body cools more slowly than a small one because the ratio of surface area to volume is smaller, less surface to radiate heat relative to the thermal mass that must cool. This is the same reason a large pot of water takes longer to cool than a small cup. The volume increases as the cube of the linear dimension, but the surface area increases only as the square. A body with more subcutaneous fat cools more slowly because fat is a thermal insulator. It conducts heat roughly one-third as well as muscle tissue. A body on a tile floor cools faster than a body on a mattress because the thermal conductivity of ceramic tile is roughly 20 times that of foam. Heat conducts away through direct contact far faster than it radiates into still air. Three mechanisms of heat transfer operate simultaneously. Conduction carries heat from the body into whatever surface it rests on, the rate proportional to the temperature difference, the contact area, and the thermal conductivity of the surface. Convection carries heat away through moving air. Even the subtle air currents in a closed room create convective cooling, and a body outdoors in wind cools faster than one in still air. And radiation, infrared emission, carries heat away as electromagnetic waves. Every object above absolute zero radiates electromagnetic energy. A living body at 37 degrees radiates roughly 100 watts in the infrared spectrum. After death, that emission continues, but no new heat is generated to replace the lost energy. The body is a cooling emitter with no power source. Forensic scientists have used this cooling curve to estimate time of death for over a century. The simplest formula, the Glaser equation, divides the temperature drop in Fahrenheit by 1.5 degrees per hour to estimate the postmortem interval. A body found at 90 degrees Fahrenheit would suggest roughly 5.5 hours since death. But this formula assumes a constant cooling rate and ignores the dozens of variables that affect heat loss. In 1988, a German forensic scientist named Klaus Henske published a far more sophisticated model, a nomogram that accounts for body weight, clothing, ambient temperature, and whether the body is in air or water. That remains the standard tool in forensic pathology today. Get the math wrong, and the wrong person goes to prison. The Henske model corrects for the fact that a large clothed body in a warm room cools on a fundamentally different curve than a small unclothed body in cold water. But the underlying physics in every model is Newton's law, the same first-order differential equation, the same exponential decay. Solved 325 years ago, now applied to the most complex thermal object a forensic scientist will ever encounter. There is one complication that puzzled early investigators. In the first hour or two after death, many bodies show a temperature plateau. The core temperature barely drops at all, even though the surface is cooling. This is not a violation of Newton's law. It is a heat transfer problem created by the body's internal geometry. The core, the deep organs, the brain, the viscera, is insulated by concentric layers of muscle, fat, and skin, each with different thermal conductivity. Heat must conduct through all of these layers before it can radiate from the surface. In the first hour, the outermost layers cool rapidly, but the thermal wave has not yet penetrated to the core. The core temperature stays nearly flat while the surface drops. The Henske model accounts for this with a correction factor that produces a sigmoid-shaped curve, flat, then steep, then flattening again, rather than a simple exponential. But the principle is the same. This is a complex, heterogeneous, roughly cylindrical thermal object cooling to ambient through multiple layers of different thermal conductivity. By 24 to 36 hours after death, the core temperature has equalized with the room. The thermal gradient that separated the interior of the body from its environment, a gradient that had been maintained continuously for an entire lifetime, is gone. That clock stops. While the thermal gradient is collapsing, a second gradient fails, and this one reveals something counterintuitive about how energy maintains mechanical systems. You might expect that when a molecular motor loses its fuel, it goes slack. It does not. It locks. The phenomenon is called rigor mortis, and the physics reveals something fundamental. In any molecular motor where the resting state is bound, relaxation requires energy. Stiffness does not. Your muscles contain billions of molecular motors, protein machines that grab, pull, and release in a repeating mechanical cycle to produce movement. Each cycle of the motor requires one molecule of fuel, ATP, to complete. And the critical detail is this: the fuel is not needed for the power stroke. The motor grabs its track and pulls. That happens spontaneously, driven by the shape of the molecule itself. What needs fuel is the release step. To let go of the track and reset for another cycle, the motor must bind a fresh ATP molecule. That binding causes a shape change that breaks the grip. Without ATP, the motor stays locked onto its track. It cannot release. The default state of the system, the state it falls to when no energy is being supplied, is locked, stiff, immobile. In every machine humans have ever built, the resting state is the relaxed state. A spring returns to its natural length. A piston returns to bottom dead center. The default is loose, not tight. But in any system where the components are bound at the energy minimum, where the thermodynamic ground state is attached, not detached, removing the energy source does not produce relaxation, it produces rigidity. The system falls to its lowest energy state, which is locked. Muscle is the most dramatic example in nature. The default state of the motor track system is bound. It takes energy to break the bond and allow movement. Rigor mortis is not something that happens to a body after death. It is the thermodynamic ground state of a molecular motor system, revealed when the energy that kept it cycling is withdrawn. An engine seizes when the oil runs dry. The moving parts bind against each other because the lubricant that allows them to slide is gone. ATP is the lubricant in the molecular motors of your muscles. When it is gone, the machinery ceases. The analogy is not poetic, it is mechanical. The physics is the same. The timeline follows fuel depletion. Small muscles have smaller fuel reserves and lock first, the jaw and eyelids within 2 hours of death, the hands within 4, the legs by 6 to 8. The entire body is rigid by roughly 12 hours. The process begins everywhere simultaneously. Every motor in every muscle fiber is depleting its fuel at the same rate. But smaller muscles have less fuel stored, so they cross the threshold first. Exactly as a fleet of cars running out of gas simultaneously would see the ones with smaller tanks stop first. After 12 hours, rigor mortis is complete. The body is rigid. And it stays that way for roughly another 12 to 24 hours. Then it begins to resolve. The muscles soften. The joints become pliable again. But this is not because fuel has returned. It is because the motors themselves are being destroyed. The same chemical dissolution that is disassembling the rest of the cell. The process called autolysis, which I will get to shortly, eventually breaks apart the motor proteins. The lock does not open. It is dissolved. There is one rare and dramatic exception. If a group of muscles was under extreme exertion at the exact moment of death, a drowning person gripping weeds, a soldier clutching a weapon, those muscles had already exhausted their fuel through the exertion itself. They lock instantly, no 2-hour delay, no progressive onset. The hand freezes in its final gesture. This is called cadaveric spasm, and forensic investigators treat it as strong evidence that the object was being held at the moment of death. Because the grip of rigor mortis can be broken by force, but cadaveric spasm cannot be reproduced after the fact. You cannot stage it. The physics only works once. The third gradient to collapse is a fluid dynamics problem. A living heart maintains a pressure gradient that pushes 5 liters of fluid against gravity through 100,000 kilometers of vessels. When the pump stops, that gradient vanishes, and the only force remaining is gravity. The blood begins to settle. Red blood cells, slightly denser than the surrounding plasma, sink toward the lowest point in the body. This is sedimentation, governed by the same physics that causes silt to settle in a river, cream to separate from whole milk, or particles to separate in a centrifuge. Stokes's law gives the settling velocity of a particle in a viscous fluid. It is proportional to the square of the particle radius, proportional to the density difference between particle and fluid, proportional to gravitational acceleration, and inversely proportional to the viscosity of the fluid. Red blood cells are small, roughly 7 micrometers in diameter, and the density difference between a red blood cell and plasma is slight, so the settling is slow. But gravity is patient, and it has hours to work. The result is called Rigor Mortis, from the Latin livor, meaning bluish color. The dependent parts of the body, whichever surfaces are closest to the ground, develop a deep purplish red discoloration as blood accumulates in the small vessels of the skin. The upper surfaces, where blood has drained away, become pale. If the body is lying on its back, the lividity appears on the back, the buttocks, the backs of the arms and legs. If the body is hanging, it appears in the hands, feet, and lower legs. If the body is face down, it appears on the face and chest. The pattern is a map of the gravitational field acting on the blood. It shows you, precisely, which direction was down for the hours after death. The settling is slow because the forces involved are small. The density difference between a red blood cell and the plasma surrounding it is only about 8%. The cells are tiny, 7 micrometers, roughly 1/10 the diameter of a human hair, and plasma is viscous enough to resist the settling. Stokes' law tells you the balance point. The gravitational force pulling the cell downward is proportional to the cell's volume times the density difference times g, while the viscous drag resisting it is proportional to the cell's radius times its velocity times the fluid viscosity. The settling velocity is the speed at which these two forces balance. For a red blood cell in plasma, that velocity is very low, but it is not zero. And over hours, even slow settling produces visible results. For the first 6 to 8 hours, the settling is reversible. Press a finger firmly into the discolored skin and the blood displaces. The cells are still suspended in liquid plasma, still inside the capillaries, still mobile. The pressure from your fingertip exceeds the hydrostatic pressure of the pooled blood column, so the fluid moves away from the point of pressure. The skin blanches white. When you release, the blood slowly flows back, driven by the same gravitational settling that put it there in the first place. This is the blanching test, and it tells forensic investigators that the lividity is not yet fixed. The blood is still in the vessels, and the body could have been repositioned recently. After 8 to 12 hours, the lividity becomes fixed. What changes is not the settling. That was essentially complete within a few hours. What changes is the containment. The walls of the capillaries, already weakened by the loss of oxygen and the onset of autolysis, begin to break down. The red-colored molecules in the blood leak through the vessel walls into the surrounding tissue. A process driven by diffusion along a concentration gradient from high concentration inside the vessels to zero concentration in the tissue outside. Once the coloring molecule is in the tissue itself, no amount of pressure can displace it. The stain is permanent. The settling was governed by Stokes' law. The fixation is governed by Fick's law of diffusion. Two different physics processes, operating on two different timescales, producing a forensic marker that tells investigators not just where the blood went, but when the walls that contained it failed. This is why forensic investigators examine lividity patterns with extreme care. If a body is found lying on its back but the fixed lividity is on the front, the body was in a face-down position for at least 8 to 12 hours before being turned over. The blood told the truth. The scene may be staged, the body repositioned, the evidence arranged, but the physics of sedimentation under gravity and diffusion through weakened membranes cannot be faked. Gravity is a patient witness, and it does not lie. The first three gradients, thermal, mechanical, fluid, collapsed passively. Heat radiated, motors locked, blood settled, no chemical reactions were required. But the fourth gradient is different. It is a chemical gradient, a kinetic barrier holding a thermodynamically favorable reaction in check. And when that barrier fails, the reaction proceeds violently. Inside every living cell, there is a reservoir of catalysts powerful enough to dissolve the cell entirely. Acids and catalysts capable of destroying proteins, fats, membranes, DNA, every molecule the cell contains. These are not foreign agents. They are the cell's own tools, used during life to recycle damaged components. But they are kept behind walls, sealed inside compartments, maintained by fuel-powered pumps. The interior of each compartment is acidic, around pH 4.5. The environment outside the compartment is neutral, around pH 7. The catalysts are optimized for acidic conditions. At neutral pH, they are sluggish. Two barriers prevent the reaction. a physical wall, and a chemical mismatch. The reaction itself is thermodynamically favorable. Given the chance, the catalyst would dissolve everything around them. What prevents it is a dam built from energy. Death removes the dam. The fuel-powered pumps fail. The compartment walls lose integrity and rupture. The acid spills into the cell, and the pH of the entire cell is dropping independently. When the oxygen supply stopped, the cells switch to a backup energy pathway that works without oxygen but is roughly 18 times less efficient and produces acid as waste. That acid is now accumulating, pushing the environment toward exactly the acidic conditions the catalysts need. The catalysts are free. The chemistry is right. Every constraint has been removed simultaneously. The reservoir empties. This is the chemical equivalent of removing a dam from a reservoir. The water was always there. The potential energy was always there. The constraint was what held it back. Remove the constraint, and the system does what thermodynamics always said it would do. In the language of chemistry, the activation energy barrier has been removed. Not by adding energy to the system, but by removing the physical separation between the reactants and the catalyst. The reaction was always energetically favorable. It was kinetically blocked. Death removes the block. The process is called autolysis, self-digestion, and different tissues dissolve at different rates, determined by the concentration of digestive catalyst they contain and how much water is available to carry the reactions. The pancreas dissolves fastest, often within hours, because its entire function during life was to produce digestive catalysts for breaking down food. It is a factory full of its own product. In death, that product consumes the factory. The liver and kidneys follow, both rich in catalytic molecules. The brain softens rapidly because it is roughly 80% water, providing an ideal liquid medium for the reactions. Dense structural tissues like tendons and cartilage dissolve slowest. They are dry, tightly packed, and contain relatively few catalysts. The eyes are one of the first external signs. The transparent lens is maintained by living cells that arrange structural fibers in a precise crystalline lattice, the spacing exactly right to allow light to pass without scattering. This is a remarkable piece of engineering. The fibers are not transparent on their own. The transparency is a property of the arrangement. The spacing between fibers is smaller than the wavelength of visible light, so the light passes through without diffraction. When the cells maintaining this arrangement die, the fibers swell and disorder. The spacing becomes random. Light scatters instead of transmitting. The lens becomes opaque, milky, and clouded. The transparency of the living eye was not a material property. It was a structural achievement maintained by continuous energy expenditure. Without that energy, the structure randomizes and the physics of light scattering takes over. The rate of autolysis, like every chemical process described so far, obeys the Arrhenius equation. Reaction rates roughly double for every 10 degrees Celsius increase in temperature. A body in a warm room dissolves faster than a body in a cold one. A body in a freezer essentially stops dissolving entirely. The catalytic reaction rates approach zero as thermal energy becomes insufficient to drive the catalytic cycles. This is why morgues are refrigerated. It is not sentiment. It is chemical kinetics. Lowering the temperature buys time by slowing every reaction rate in the system. By 12 hours, the internal organs are softening. The barriers between compartments within cells are gone. The barriers between cells are going. And the largest barrier of all, the one between the body's own tissues and the 38 trillion organisms living inside it, is dissolving. The chemical gradient was the fourth to collapse. The fifth is biological, and it is the most extraordinary barrier in the human body because it is not a wall, it is a standing wave of energy. Your gut contains roughly 38 trillion bacteria, approximately one for every cell in your body. During life, they are confined to the interior of the intestine, held behind a barrier 1 cell thick. That barrier is not a wall made of inert material. It is a wall made of living cells, burning fuel every second to maintain the chemical connections that hold them together, backed by acid, chemical defenses, and an immune system that consumes roughly 20% of the body's daily energy budget just to keep these organisms contained. The bacteria are not invaders. They are residents. They help digest food, produce vitamins, and protect the gut from genuinely dangerous organisms. But they are held in place by continuous energy expenditure. The barrier between the bacteria and the rest of you is not a structure, it is a process that runs on fuel. This is a fundamentally different kind of containment than the compartments inside each cell that hold the digestive catalysts. Those were small, sealed vesicles, molecular bags held shut by membrane tension. The gut barrier is an entire organ, one cell thick, stretched across a surface area of roughly 32 square meters, the size of a small studio apartment. Every cell in that barrier is burning ATP to maintain its connections to the cells beside it. Every cell is being replaced every 3 to 5 days. The entire barrier is rebuilt from scratch once a week continuously using energy. If you stop feeding a living person, if you cut off all food and water, the gut barrier would be among the first structures to fail, simply because it has the highest turnover rate and the highest energy demand per unit area of any tissue in the body. Death withdraws the fuel. The cells of the gut wall run out of energy. The connections between them dissolve. The same autolysis that is destroying every other cell is destroying the barrier cells too. The acid in the stomach stops being produced. The chemical defenses cease. The immune system, which required oxygen and ATP to function, goes silent within minutes. And the bacteria, which thrive without oxygen, find themselves in a suddenly undefended landscape of dissolving tissue. They migrate out through the blood vessels that once supplied the gut wall. The first organ they reach is the liver, because the portal vein carries blood directly from the gut to the liver, and the bacteria follow the plumbing. From the liver, they spread through the circulatory system to every organ. The path of migration is the path of the blood vessels, now stagnant conduits filled with settled blood and no flow. The bacteria do not need to bore through tissue. They simply follow the existing infrastructure. The same vessels that once carried oxygen and nutrients now carry organisms. Within 12 to 24 hours, bacteria that spent their entire existence confined to the inside of a tube are colonizing the lungs, the brain, the kidneys, the muscle. The first visible sign of this invasion is a greenish discoloration of the skin over the lower right abdomen, where the cecum, the most bacteria-dense region of the gut, lies closest to the skin surface. The green color comes from a chemical reaction. The bacteria produce hydrogen sulfide gas as a metabolic waste product, and when that gas contacts the iron-containing molecule in the blood pooled in the nearby vessels, it produces a green compound. The patch typically appears 12 to 24 hours after death in temperate conditions. In hot environments, it can appear in half that time. What follows is an ecological succession, the same pattern that ecologists observe when any ecosystem is disrupted. A forest burns, a lake is polluted, a coral reef bleaches. In every case, the sequence of organisms that colonize the disturbed environment follows a predictable order, determined by which organisms can exploit the current conditions and how they change those conditions for the next wave. The same mathematics applies inside a dead body. The first colonizers. The gut bacteria transform the chemical environment. They consume whatever oxygen remains. They lower the pH by producing organic acids. They break down complex protein and fat molecules into simpler compounds, releasing nutrients that were locked inside tissue structures. This creates conditions favorable for the next wave of organisms, different species adapted to the new chemistry. Each wave changes the environment for the next. Each wave is a predictable chapter in a sequence that has been studied in forensic science for over a century. The mathematics is population dynamics. Under favorable conditions, warm temperature, abundant substrate, no immune opposition, gut bacteria can double every 20 to 30 minutes. A single doubling from 38 trillion to 76 trillion already represents an increase of 38 trillion organisms. 10 doublings, achievable in 5 to 6 hours, would multiply the population by roughly 1,000. The growth is exponential at first, then decelerates as the population approaches the carrying capacity of the environment. And as they consume, they produce gas. This is fermentation, the same thermodynamic process that produces beer from grain, wine from grapes, yogurt from milk, and sauerkraut from cabbage. Organisms consuming organic material in the absence of oxygen, producing simpler molecules, organic acids, and gas as metabolic waste. The body is a fermentation vessel. The chemistry is the same. The physics is the same. The only difference is the vessel. The gases are specific and identifiable. Hydrogen sulfide, the compound responsible for the smell of rotten eggs, produced by the bacterial reduction of sulfur-containing amino acids. Methane, produced by specialized organisms that consume the waste products of the first-wave bacteria, converting organic acids into methane and carbon dioxide. Ammonia, released when the nitrogen-containing amino group is stripped from amino acids during their breakdown. Carbon dioxide, a universal byproduct of metabolic respiration, aerobic or anaerobic, and two molecules with names that leave nothing to the imagination, cadaverine and putrescine. Cadaverine is a 5-carbon chain with an amino group at each end, produced when bacteria remove the acid group from the amino acid lysine. Putrescine is a 4-carbon chain with the same structure produced from ornithine. They are named for exactly what they smell like. Their chemistry is straightforward. What happens next is a straightforward application of the ideal gas law, one of the first equations taught in any physics course, now operating inside a sealed biological cavity. These gases accumulate inside the body. The abdominal cavity is roughly sealed. The skin and muscle wall form a container, and the gases produced by bacterial fermentation in the gut have no exit. The ideal gas law describes what happens next. Pressure equals the number of gas molecules times the gas constant times the absolute temperature divided by the volume. As bacteria produce more and more gas molecules inside a roughly fixed volume, the internal pressure rises. At first, the pressure simply distends the abdomen. The abdominal wall is elastic and stretches. The gut loops, already swollen with bacterial gas, push outward. The diaphragm is pushed upward into the chest cavity and gas migrates into the subcutaneous tissue throughout the body. The face swells, the tongue protrudes, the eyelids puff shut, the body can expand to nearly twice its original volume. But the gas production does not stop, and eventually the internal pressure exceeds the tensile strength of the tissues. The weakest points fail first, typically the abdomen, where the wall is thinnest and the pressure is highest. The body ruptures. Fluid and gas purge through the point of failure and through natural openings. The release of pressure produces a rush of the gas compounds that had been accumulating under compression, and the odor, already detectable from a distance, becomes overwhelming. The chemistry is the same as opening a pressurized fermentation vessel. The physics is the same. Every chemical reaction driving this process obeys the Arrhenius equation, the fundamental law relating temperature to reaction rate. The equation states that reaction rates increase exponentially with temperature, not linearly. This is an important distinction. A 10-degree increase does not add a fixed increment to the rate, it multiplies it. As a practical approximation, biological reaction rates roughly double for every 10 degrees Celsius of warming. This compounding effect means that small temperature differences produce large rate differences. A body at 30 degrees Celsius does not decompose 50% faster than a body at 20. It decomposes roughly twice as fast. A body at 40 degrees decomposes roughly 4 times as fast as one at 20. The exponential nature of the relationship is why temperature is the single most important variable in forensic decomposition analysis. It overwhelms every other factor. A body in a car in summer, interior temperatures easily reaching 50 to 60 degrees in direct sunlight, can reach the bloating stage in 12 to 18 hours. A body in a cool basement at 15 degrees may not bloat for a week. A body in a freezer at -10 degrees can remain essentially unchanged for months or years. Every reaction rate driven so close to zero that the decomposition process effectively stops. A body recovered from a glacier can be intact after thousands of years. Tzi, the Iceman, found in the Alps in 1991, died roughly 5,300 years ago, and his skin, organs, and stomach contents were preserved well enough for detailed scientific analysis. The Arrhenius equation explains why, at the temperatures inside a glacier, the chemical reaction rates responsible for decomposition are effectively zero. Time does not matter if the rate is zero. The equation does not care how many years have passed. Only the temperature matters. There is a forensic rule of thumb called Casper's rule, proposed in the 19th century. 1 week of decomposition in air is roughly equivalent to 2 weeks in water and 8 weeks buried in soil. The differences are driven by temperature, oxygen availability, and microbial access. A body in water is typically cooler and has less oxygen available. A body in soil is cooler still and has even less microbial access. But the underlying principle is always the Arrhenius equation. Every step of decomposition is a chemical reaction. Every chemical reaction has a rate that depends exponentially on temperature. One equation, published by Svante Arrhenius in 1889, governs the pace of every process described so far. The insects provide the most precise demonstration of that equation in all of forensic science. Within minutes of death outdoors, volatile chemical compounds from early tissue breakdown attract the first wave of insects. They lay eggs at accessible sites, openings, wounds, any surface where tissue is exposed. The eggs hatch in 24 to 45 hours, depending on temperature. The emerging larvae secrete their own digestive catalysts onto the tissue surface, dissolving it into liquid before feeding. They do not chew, they dissolve. And they grow rapidly, passing through several developmental stages over the following days, increasing in size by orders of magnitude. The rate of that growth is a precise function of temperature, the same Arrhenius relationship that governs every other chemical process described so far. The larvae are, at bottom, chemical reactors. Their growth is driven by catalyzed reactions, the same kind of reactions that drive autolysis and bacterial fermentation. Warmer temperatures accelerate the reactions. Cooler temperatures slow them. The relationship is exponential, not linear. Forensic scientists exploit this precision using a concept called accumulated degree hours. The idea is simple. Each hour of the larva's life is weighted by the temperature during that hour. A warm hour counts for more developmental progress than a cool hour. The total warmth the larva has experienced, the sum of all those weighted hours since it hatched, determines how far it has developed. Each species has a known total warmth requirement for each developmental stage, established through controlled laboratory experiments. If a forensic entomologist finds larvae at a particular stage, identifies the species, and knows the hour-by-hour temperature history of the site, available from the nearest weather station, then the calculation runs backward. How many hours of that specific temperature history would it take to accumulate the required degree hours? That number is the minimum time since the eggs were laid. And since the eggs are typically laid within hours of death, that minimum is very close to the time of death itself. The precision is remarkable. In controlled studies, the method can narrow the post-mortem interval to a window of hours, even when the body has been dead for weeks. No other forensic method achieves this accuracy at post-mortem intervals greater than 3 days. After 72 hours, the classical methods of estimating time of death have all reached their limits. The body has cooled to room temperature. Thermal clocks stopped. The muscles have fully stiffened and begun to soften. Mechanical clocks stopped. The blood has pooled and fixed. Gravitational clock stopped. But the insect clock is just getting started. It will keep running for weeks. After the first wave of insects, a second arrives, attracted by different chemicals produced at a later stage of decomposition. Then a third. Then a fourth. Each wave is a timestamp. Each species is a signature of the chemical conditions at the time it arrived. The succession of insect species on a body is as predictable as the succession of plant species in a cleared forest. And forensic entomologists read it the same way ecologists do, using the community of organisms present to reconstruct the history of the ecosystem. One final detail about the insects that belongs in a physics discussion. When larvae feed in large numbers, they pack together into dense masses, sometimes thousands on the same area of tissue. These masses generate their own heat through metabolic activity. The temperature at the center of a large larval mass can exceed the surrounding air temperature by 15 to 20 degrees Celsius. The larvae are creating their own microenvironment, a warm, moist, catalyst-rich zone that accelerates their development and the dissolution of the tissue beneath them. This is a positive feedback loop. More heat accelerates the chemical reactions inside each larva. Faster reactions increase metabolic output. Greater metabolic output produces more heat. The larval mass is a self-heating chemical reactor. It is also a complication for forensic timing. Because the larvae experience a higher temperature than the ambient air, their accumulated degree hours are higher than a simple weather station reading would suggest. The entomologist must account for the thermal contribution of the mass itself. The physics is circular. The organism's growth rate depends on the temperature, but the temperature depends on the organism's growth rate. At the beginning, I told you that a living body is a dissipative structure, a system whose order exists only as long as energy flows through it. Every section since then has been one demonstration of that principle. 80 watts. Every second. For an entire lifetime. Over 70 years, that is roughly 50,000 kilowatt hours, the energy equivalent of 5,000 liters of gasoline or 150,000 kilometers of driving, consumed entirely to maintain the pattern that was you. Thermal gradient, Newton's law of cooling. Mechanical gradient, molecular motors falling to their bound ground state. Fluid gradient, Stokes's law of sedimentation under gravity. Chemical gradient, kinetic barriers removed from thermodynamically favorable reactions. Biological gradient, an energy-dependent barrier collapsing and releasing a constrained population. Pressure gradient, the ideal gas law in a sealed cavity. Rate of every process, the Arrhenius equation. 7 gradients, 7 laws, each collapse inevitable, each rate calculable, and each one telling you something about what the living body was spending energy to prevent. The cooling tells you the body was generating heat. The stiffening tells you the motors were being actively relaxed. The self-digestion tells you the catalysts were being actively contained. The bacterial invasion tells you trillions of organisms were being actively held in check. Every stage of decomposition is a measure of something the living body was doing, every second of every day, for decades. And the order of collapse reveals the energy cost of each gradient. Neural activity, consuming 20% of all energy despite the brain being only 2% of body mass, fails within seconds of oxygen deprivation. The heartbeat follows within minutes. Cellular chemistry persists briefly on backup fuel reserves, then fails. Membrane integrity degrades over hours. Protein structure degrades over hours to days. Connective tissue degrades over weeks to months. And bone mineral, a crystal lattice of calcium and phosphate that requires no energy whatsoever to maintain its structure, persists for centuries. Millennia. We find fossils because bone mineral is the one structure in the body that sits at thermodynamic equilibrium during life. It costs nothing to maintain, so it costs nothing to persist. The structures that cost the most energy to maintain are the first to fail. The structures that cost nothing persist longest. The order of decomposition is a direct readout of the energy budget of life. In another video, I told you where those atoms go when the pattern is finally dismantled. The carbon becoming CO2, the hydrogen and oxygen becoming water, the nitrogen rejoining the atmosphere, the calcium remaining as mineral dust. The atoms remain. They always do. But what I did not tell you is what happens before they leave. Right now, as you hear this, your body is spending 80 watts to hold every one of these gradients in place. The heat, the motors, the barriers, the walls, 80 watts every second. That is what it costs to be you. That is how it works. That is physics.